Hello everyone and welcome to my latest Rust Quickie. In my last Rust Quickie I have talked about the stack. You have seen that local variables are always allocated on the stack, and today I want to continue that discussion by talking about the heap in Rust. Again, I'm just assuming that you have a basic understanding about the heap, so please refer to that Wikipedia article about more information about the heap itself. So let's switch over to Visual Studio Code, where I want to talk now about heap management in Rust. Let's have now a look how you can work with the heap in Rust. As I have said in my last Rust Quickie, all local variables in Rust are always allocated directly on the stack within the stack frame of our current executing function. So the question is now, how can you allocate some memory on the heap? In Rust, this is very simple because you have this so-called box structure. A structure is more or less a more complex data type, and you can put some value into a box, and that value within that box object is then allocated on the heap. Means in our case we are putting here the value, the integer value of 42 into a box object, means that the Rust compiler internally allocates that value on the heap, and finally we are storing that value into a local variable. It's the same here. I'm allocating here a tuple on the heap. So we have here two integer values, the value of 5, the value of 4. They are in parentheses, means we are talking here about a tuple, and that tuple is again allocated on the heap. And we are storing that allocation in a local variable. So that local variable just points to the value on the heap. So by now, you already know how you can allocate memory on the heap in Rust. When you're working with system programming languages like C and C++, you know when you allocate some memory on the heap, you also have to deallocate that memory. So you have to do a free operation in C or a delete operation in C++, otherwise you are ending up with a memory leak. When you are working with managed languages, for example with the .NET framework or with Java, you know that those managed languages, they have a garbage collector. Means the garbage collector just runs periodically and just deallocates memory on the heap that is not needed anymore automatically for you. So the question is now, how handles Rust memory deallocations? Do you have to do memory deallocations manually, like in C, C++, or is Rust using a garbage collector, like managed programming languages? Well, the answer is easy. Rust is not doing both things. You don't have to deallocate memory manually, and Rust also doesn't have a garbage collector, because in Rust, memory is always deallocated immediately when the memory is not needed anymore. And therefore there is no reason for a garbage collector, which again improves the performance. Every memory that you are allocating in Rust on the heap has only one possible owner. We are talking about the ownership concept in my next Rust Quickie, and as soon as that owner goes out of scope, the memory is immediately deallocated. So when we are looking at those proof memory allocations, the owner of that value 42 on the heap is that variable called integer value, and the owner of that tuple that we have allocated here is that local variable. And as soon as those two local variables are going out of scope, at the end of our function, the heap memory is released automatically by the Rust code. As you already know, when we are leaving a function, the stack frame is destroyed. Means when we are destroying the stack frame, we are destroying both two local variables, and therefore the Rust compiler automatically just releases the memory which was allocated on the heap. So this is very, very powerful in Rust, because there's no chance for memory leaks by default, and you also don't have the overhead of a garbage collector, because you always know precisely when Rust is deallocating memory. When you are working with Java, when you are working with the .NET framework, the garbage collector just runs periodically in the background, and during that garbage collection run, you have a performance impact. But that is not the reason with Rust, because we know deterministically when memory is deallocated. Let's have a look on that one. Let's just disassemble that function work with the heap. So let's do that with the cargo awesome command. Let's go up to the beginning of the disassembly. And as you can see in the first step, we are setting up a stack frame. And as you can see now, we are calling here now an internal function called Rust alloc. Means that function allocates now some memory on the heap. We are doing here the call to that function. Rust compiler, of course, prepares all the necessary input parameters to that function call. And then in the next step, we are just testing the return value, which is always stored in the rex register on a 60-bit for CPU architecture. With the test call, we are just testing if we have a null pointer. So when we are getting back a null pointer, we know the memory allocation didn't happen, and we are jumping to that label LPP9_9. Let's search that one. It's a little bit below, hopefully, which is here. We have here that label, and as you can see, we are handling here that allocation error from the heap. Let's go back up. So we have here that first call to Rust alloc. As you can see, we are moving afterwards the value of 42 into heap memory. Very, very important. That value is not stored in the stack frame. The stack frame just stores the pointer to the heap value itself. And in the next step, when we go down, we have our second call to Rust alloc, which is used to allocate some heap memory for the tuple values that we are storing here. Again, we have a test of a null pointer, and afterwards we are moving that tuple value into that heap location, heap memory location that we have allocated. And let's go down now a little bit. Let's go down. And as you can see here now, as soon as those two local variables are going out of scope, the heap memory is released automatically by the Rust compiler. So the Rust compiler just calls an internal function called Rust dealloc, and that function just deallocates the memory that we have previously allocated when we have created that box object. So this is very, very important. You know deterministically when the Rust compiler releases memory for you. There's no garbage collection which causes you a performance impact, and you don't need to deallocate heap memory on your own, like in C and C++. Means Rust is also a memory safe language, because by default, when you're just working with safe Rust code, you have no possibility for memory leaks. So we have here our first deallocation. And when we go down, we have the second deallocation, because of course we have done 2 allocations on the heap. So this is very, very important. And at the end, we have the epilogue, which just destroys our current stack frame. So very, very important. All those things that we have covered here today. And as I have said, every memory that you are allocating on the heap has just one possible owner. This is also very, very important, and therefore we will look next week into the so-called ownership concept in Rust and into so-called move operations. So very, very important things that you have to know in Rust, because they are very, very specific to Rust. Okay, so thanks for watching my today's Rust Quickie. I hope that you have learned again a lot of new things about Rust, and I'm already looking forward to see you next week again, where we will talk finally about the ownership concept in Rust. So thanks for watching, stay tuned, and see you soon. Thank you.